So the title is Next Horizons, and when I originally prepared this talk and gave it, was just after Pluto, after the flyby of New Horizons past Pluto. So this was the New Horizons rocket, and sitting there on the launch pad, and it was launched on the 19th of January 2006. A very successful mission, and it took a long time to get out to Pluto. Pluto orbits are on average 13.5 astronomical units from the Sun, and it has a journey time of just under 9.5 years to get there, doing various slingshots and things like that past Jupiter and so on the way out there. That's a 3 billion mile journey. The flyby took place on the 14th of July, and by this time the craft had built up to 12.5. It passed Pluto at 12,500 kilometers above the surface. So there's some really good pictures that were taken. And at the time of going past, it was 4.5 light hours from the Sun. So this was the image that was taken of Pluto at the time, and some of the large sort of blocky ice mountains that were seen there on the surface. And Pluto has an atmosphere, and very likely has snow on the surface from this atmosphere. So the thing is, where do we go next after Pluto? Where did the craft go after that? Well, it the next thing it went to was something called 2014 MU69. Now, it actually had a series of names. It was discovered on the 26th of June 2014 by the Hubble Space Telescope, and so you can see it here in the picture. 2014 MU69 was the official sort of numerical designation as to when it was discovered and where it is and what kind of object it is, all encoded in that name. But they were looking for somewhere for New Horizons to go on to after it had passed Pluto. And the PT1 that's at the bottom here stands literally for Potential Target 1. And it's the object was very faint when it's first discovered at magnitude 26. They eventually named it Ultima Thule, and this was the name that was proposed by people in the public. It turned out that this name actually had some rather unfortunate historical context, because it was a name that apparently was used by the Nazi Party during World War II. So in the end, they decided to call it Akoff, which is, I think, a name for one of the deities in North American Indian tribal law, the Palanquins or something. Now, MU69 orbits 44.2 AU out, with a long orbital period, low inclination and eccentricity, classic Kuiper Bell object, with a diameter that's estimated at about 30 to 45 kilometers. So this was the sort of path that was taken out. It turns out that it's not a lot further out than Pluto, and the flyby eventually took place on the 1st of January 2019. So this was an artist's impression of what looking back at the Sun would look like from Akoff. And this was the flyby, which eventually was at 43.4 AU from the Sun, and this is what was seen. This is again typical of a Kuiper Bell object with this sort of reddish color. This is an accurate color representation of the surface, and it's clearly a contact binary where two lumps have collided together at very low velocity, and low enough velocity that it didn't cause either of the two bodies to break up, but the two collided and stuck, a bit like billiard balls coated in honey, and they sort of joined together and stuck. And so you can see it has this rather odd shape. And interestingly, of course, similar sorts of shapes seen for the comet that was studied on the Rosetta mission, 67P Churyumov-Gerasimenko, which has this similar sort of plastic bathtub duck shape. But where next? Where might we go on to after we've got out to the edges of the solar system? We obviously have some of the Voyager spacecraft now as the furthest objects away from the sun, man-made objects from the sun. We have to ask the question: where would we like to go? Maybe we'd like to get to the nearest star. That would be great to get to Proxima Centauri. Maybe just get to an interesting star, a binary or a red dwarf or something like that. Maybe we'd like to get to see an Earth-like exoplanet up close. Maybe we'd like to get across the galaxy, see what's the other side of the center of the galaxy that we can't see from here. Too many stars, too much dust and gas in the way. Maybe we'd like to get to another galaxy, the Andromeda, that sort of fuzzy patch that we can see in the night skies. It would be fun to be up there and look back at our Milky Way galaxy from Andromeda. Well, can we? Can we do that? So I'm going to show some numbers here. I've got also coming up three equations, but four, but very, very simple ones. So let's assume that you're going to do a journey in a rocket ship. I'm not saying it looks like the one in the top right-hand corner of the picture here, but let's assume we're going to do the journey in a rocket ship, and we're going to have an acceleration of 1g, so that an astronaut in the rocket ship is pressed to the floor of the rocket ship in the same way that when you stand up, you're pressed to the floor.
Somebody at the door. Sorry, I'll have to just nip. Sorry.
Now, it turns out that this acceleration of 9.81 meters per second, which is increasing your speed by 9.81 meters per second every second, it corresponds to just over 1 light year per year. And so for those of you who are thinking about the numbers here, that should already be ringing alarm bells, but I'll come back to that later. So here's three of the equations. These are the very simple sort of Newtonian equations, which say that if you travel with an acceleration a for a time t, this is the distance you will go. Or you can turn this equation inside out, and you can say that if you travel a distance d with an acceleration a, this is how long it will take you. And if you travel an acceleration a for a time t, this is the velocity you'll have by the time you get there. So let's look at some typical destinations that we might have. We've got Pluto at 0.00063 light years. I had to count how many zeros I'd said. We've got Proxima Centauri, and going all the way out to the Andromeda Galaxy. I won't code it to the nearest light year, but I've got 2.5 million down here as a representative sort of number for a distant galaxy. So how long will that take doing this, looking at these basic sort of schoolboy equations that you do in physics and maths at school? Well, it turns out it's quite a long time. Although surprisingly, not as long as you would think, according to this very simple measure. Just over 2/3 to get to the Andromeda sounds like something that you could do with a few generations, or getting out to Proxima Centauri and back again in time for England to next win the Ashes or something like that. It looks like it's doable. The speed that you would have accelerating all of this time, however, is getting to be quite big. If you accelerate continuously at 1g for all of this time, and you can see straight away there is a problem here, because the speed of light, by definition, is 1 light year per year. And yet here we're talking about speeds already, even for getting to Proxima Centauri, of nearly 3 light years per year, 3 times the speed of light, let alone down here for Andromeda. Clearly, since you can't go faster than the speed of light, there's clearly something we've got to revisit. You have to start thinking about relativity. Now, in the equations on relativity, there's this value gamma, which quite often comes up, and basically this is just your velocity, and this is the speed of light. And this is a number. The graph shows it here. This is just a value where, if you have a certain percentage of the speed of light, this value of gamma stays relatively low most of the time, and then suddenly zooms up and shoots up towards the end. What it means here is that the time on the rocket, this is the time dilation issue that you have from relativity, where if you were to get your rocket up to say 70 or 80% of the speed of light, then it means typically someone on the rocket will age at 2/3 of the rate of someone back on Earth. The other problem, and one that's particularly salient here for this this little chat, is that the mass of the rocket also increases as it goes faster and faster. So that here again, if you're getting up to sort of 80% of the speed of light, then the mass of the rocket will be getting up to something like 1.5 times what the mass of the rocket is when it's at rest. So as the mass of the rocket goes up, whatever you're doing to accelerate it and make it go faster gets harder and harder and harder. As you go faster and faster, you need more and more work to get that rocket to go faster. And you're on a losing streak, because as you get closer and closer to the speed of light, where the mass goes up and up and up, you start to tend towards needing almost infinite amounts of energy to actually get to go faster. That's why you can't get bodies that have a mass to go faster or as fast as the speed of light, and certainly not faster than the speed of light. So how do our numbers change? Well, here we are now. We've got the time here on Earth. This is the time of your journey as perceived from Earth. You're traveling at for most of the journey at close to the speed of light, and getting up towards the speed of light for something like Andromeda. So from Earth, you take only slightly longer than light takes to get there. But for somebody on the rocket, you can see that for the lifetime of a person on the rocket, it's potentially doable. Again, Proxima Centauri is there and back. Not quite in time for tea, but a reasonable journey, certainly capable within someone's lifetime. And we have even getting to the Andromeda galaxy, even though 2.5 million years will have elapsed on Earth, the person on board your spacecraft accelerating at 1g all of that time, experiencing that force, will only have aged about 15 years. However, look at the speed. By the time you get there, you're traveling almost at the speed of light. I mean, it's very, very nearly there. But this is for a fast flyby. This is where you would arrive at Andromeda, and you'd probably only have a very short space of time before Andromeda is now in your spacecraft's rear view mirror. I'm assuming you have a rear view mirror in a spacecraft, or maybe if not wing mirrors, and you can see the Andromeda Galaxy receding behind you, because you didn't get a chance really to do anything when you were there. No chance to meet aliens and have tea with them and tell them what life's like back on Earth. And of course, the other thing too is that by now you're traveling so close to the speed of light that all of your signals back to Earth, not only are they going to take 2.5 million years to get back to Earth, but they're very, very, very highly redshifted. So you'd have to be broadcasting using modulated gamma rays or something like that for them to be picked up as radio waves here back on Earth. So that's clearly an issue, and really you'd like to get more out of this. So what happens if you sort of go halfway, and halfway there you flip your rocket round, and then you use your engines to decelerate so that you can come to a stop by the time you get to your destination? Well, it makes the journey a bit longer, as you might expect. Your journey to the Andromeda Galaxy goes up to 28 years. So this does at least give you a chance to do something useful. And it also means, of course, that your signal's not redshifted to come back to Earth. You can't do much about the fact that it's still going to take 2.5 million years for the signal to get back to Earth. And I would guess that by the time you get there and have something interesting to say, by the time your signal gets back to Earth, just over 5 million years, or it's about 5 million years after your departure, they will have stopped sending out the search parties. But this is all just fiddling with numbers. What about the practicalities of getting there? Let's consider our options. We have chemical fuel, like solid fuel boosters, and Elon Musk's using methane and oxygen, liquid methane and oxygen, to launch his rockets. So that's an option. What about nuclear fuel? Well, nuclear in itself doesn't provide thrust, but maybe you can take some gas and get it really hot using nuclear energy and blast it out the back to give your rocket some thrust. maybe we could have a different kind of nuclear. We have antimatter annihilation. Let's just suppose that, like Mrs. Beaton said, first catch your blackbirds, maybe, first make your antimatter. But supposing we could, and let's suppose that we could find a way of safely storing it so that we didn't actually end up annihilating our spacecraft. Suppose we could take matter and antimatter and we could combine that to produce energy and produce thrust. Let's assume that maybe we can turn all of that into energy. Maybe we could fire lasers out of the back of the rocket ship, and we could use the reaction produced by firing these high energy photons out of the back to give us an acceleration going forwards. And then, of course, then we're into the Star Trek. This is the speculation: warp drives, wormholes, black holes, the slingshots, and things like that. Well, they're fantasy at the moment. But let's see. So let's assume we can convert matter to energy. I think of all of those, matter-antimatter conversion is one possibility. Let's assume that we can convert matter to energy with 100% efficiency. For a given amount of mass, we've got multiplied by the square of the speed of light, and that's the energy, E equals mc squared. There's a lot of energy you can get by destroying a kilogram completely of matter and antimatter. How much matter do we need? Well, back to our table here again. We want to achieve an acceleration of 1g for the journey, and this is the amount of fuel you would need to have to be destroyed completely, so per kilogram of payload. So to get to Pluto, not too bad. There's only 50 grams of matter would need to be destroyed to get you out to Pluto in a reasonable time. To get to Proxima Centauri, you would have to carry 37.5 kilograms of matter to be completely destroyed, to provide you with the energy to accelerate your spacecraft to get to Proxima Centauri in a reasonable time. But you can see that the problem is, because your craft is getting more and more and more massive as you go faster and faster, you need more and more energy to get that little bit faster, to go that little bit further towards the speed of light. So the amount of energy, the amount of matter that you would have to destroy to get to the Andromeda Galaxy with 100% efficiency in the conversion is, well, you can see here, it's over 6.5 billion tons of matter. And that's not a practical rocket, I don't think, in anybody's terms. You would probably have to somehow convert the whole of the continent of the United States into energy or something like that. Some people might want to. So the engine fuel problem is it's not possible. You really can't sensibly go very, very long distances by destroying things like matter to do that. Do we have to wait for the Star Trek solution? Maybe we could do it by going more slowly. It'll take longer to get there. Maybe we could do it using robotic missions. Maybe we could do it by sending families and having generations of humans on slower traveling spacecraft. Shielding, however, becomes an issue, because as you go faster and faster and faster on your journey to get there, interstellar dust is a problem. You have to have some pretty good shields at the front of your craft, because at the faster you go, the more effect the impact of these particles on the front of your spacecraft has. And get up to a certain speed, and the nose of your spacecraft is going to be glowing red hot all of the time. But as you go faster and faster, even the impact of the energy from the cosmic microwave background falling on your spacecraft becomes an issue. There comes a point where the amount of energy from the CMB on the front of your spacecraft, even that will heat your spacecraft up to the point where you could melt or evaporate. And then returning your signals to Earth. The further and further away you get, yes, while you're traveling fast, you've got the redshift problem, but also you think about the size of the dish you're going to need and the power you're going to require to get any signal back to Earth. You'd have to consider this as a round trip where you come back to tell people on Earth all about it. They, of course, your relatives will have gone, and the institutions that you were doing this for have probably long gone. Maybe even the Earth will have gone by then. But that's a whole different talk, I think. And of course, you've also got the delay between your departure and the signals getting back to Earth. People may have well long forgotten about you by the time they receive notice. So this was a very short talk, and I hope it hasn't disappointed too much of you. But it just goes to show that the possibility of getting even to the nearest star is not a trivial one. There's quite a lot of maths in this paper. And if anyone is interested, the link to it is already on the Guildford Astronomical Society website, and the earlier version of this talk is on the Guildford Astronomical Society website. But I shall make this one available on YouTube. And thank you very much.